Good morning everyone. Today I'll be presenting a concept video on volume as double integral. It is a part of AAT concept video. My name is Zavista and my roll number is 24951A12C8. I am from Information Technology branch and this course is known as Differential Equations in Vector Calculus. Introduction to volume as a double integral. Today, we'll explore volume as double integral, a concept that extends our basic understanding of integration from 2D areas to 3D areas. Visualizing this is very useful in fields like engineering and science, where precise volume calculations are critical. Single variable integration for area. Let's quickly review single variable integration, which we know is used to find the area under the curve. First, we have to define an integral, which is this integral of a to b, f of x to dx, which gives us the area from x is equal to a to x is equal to b. Then we have to remain sums. These approximations the area by adding up the little rectangles under the curve, which is sigma of fi xi delta x. And of course the fundamental theorem of calculus, concepts, differentiation and integration, making calculations much easier. Double integrals, extending to 3D space. Now we extend this idea to a 3D space. Instead of just one variable x, now we have to integrate a function f of x comma y over a region R in an xy plane. So it is a 3D structure. Our double integral looks like double integration R f of x comma y dA, where dA represents a tiny piece of area, either dx dy or dy dx. We also use Fubini's theorem, which allows us to split a double integral into two single variable integral, making it easier to compute step by step. Choosing the order of integration, whether we have to do it first from x to y or y to x, can sometimes make a big difference in simplifying this work. So we learned about double integrals and single integrals. Now we are going to learn about geometric interpretation of volume. So what does double integral mean grammatically? If a function x comma y is a positive function, then the double integral gives the volume between the surface. Here we can take the surface as z and f of x comma y and the xy plane. Second is negative values. If x comma y is negative, it represents volume below the xy planes. In other words, a sign volume, which is in negatives. And the general volume formula. The general volume formula we use here is a double integral of r f of x comma y dA. So we learned about geometrical interpretation of volume in this slide, which includes positive functions, negative values, and volume formulas. Now we're going to jump into computing volume. Example 1. Let's look at this example, okay? So suppose we have the surface, which is z, x square plus y square over the rectangle R, whose limits are 0 to 1 and 0 to 2. So we're gonna do integral setup. It's gonna be double integration rx squared plus y squared dA, where dA is the small area. And now computing limits, we have of rectangle. One limit goes from 0 to 2 and second limit goes from 0 to 1. From x square y square dx dy. Now if we integrate, we're going to integrate 0 and 1 first with respect to x and 0 and 2 second with respect to y. So when first we integrate with respect to x and then we integrate with respect to y. After solving, we find out that the final volume is 8 by 3. Computing volume example 2. Here's another example, but the time the region is a circle. So x square y square is less than 4. What are we gonna do? We're gonna take a z as surface region. We're going to bring 4 to the LHS side, which is 4 minus x square minus y square. And now we're going to use polar differentiation. In polar, we use x is equal to r cos theta and y is equal to r sin theta and dA is equal to r dr d theta. Here the integrals are going to go from 2 pi to 4 minus r square. And when we solve it, the surface is z, which is 4 minus x square minus y square. Since we are dealing with a circle, it's easier to use polar coordinates. So after computing everything, the integral becomes 0 to 2 pi, 0 to 2, 4 minus r square, r dr d theta. First we are going to integrate with respect to dr, and then we are going to integrate with respect to d theta. After solving the whole, we are going to get a pi as our final answer. Let's see some of the applications. Volume of a sphere, sphere equation, upper hemisphere, and volume calculation. Another interesting application is to find the average height over a region. The formula is average height is equal to half area into double integral r f of x comma y dA. For example, we can use it to measure the average temperature across a metal plate. This idea is super important in physics and engineering. When studying now, materials behave under different conditions. We have studied that the materials behave different in certain conditions. So these applications are very important in the application of average height and volume of a sphere. We know that sphere equation is x squared plus y squared plus z squared defines the sphere. For upper hemisphere, z is equal to r square minus x square minus y square forms the hemisphere. Volume calculation. Volume calculation is always given in form of 2 into double integral under root x square minus y square minus r square dA is equal to 4 by 3 pi r cube. Now we're going to learn about advanced applications. Um, Now let's apply this idea to find the volume of a sphere. The sphere is defined as x squared plus y squared plus z squared is equal to r squared. The upper hemisphere can be defined as by the function z is equal to r squared minus x squared minus y squared. Using the double integral and symmetry, we can find the volume. Volume is equal to 2 into double integral under root r squared minus x squared minus y squared dA is equal to 4 by 3 pi r cube. The formula is familiar to most of us. This is for the volume of sphere. This is an application of volume of sphere. Now we are going to learn about application of average height. Another interesting application of finding the average height over a region. The formula is average height 1 by half area of r into double integral of x f of a function x comma y d. For example, it could measure the average temperature across a metal plate. Now we're going to learn about advanced application, density and mass. Moving to a more advanced application, we have density function, mass computation, and its applications. Suppose we know the density of a function that tells us how mass is distributed. So P dou of x comma y comma z describes how mass varies in volume. Mass computation is often defined by triple integration, since we have three variables here, which is dou of x comma y comma z dv integrating over an entire object. And then these techniques are critical in material sciences and structural engineering. To wrap up, or as in conclusion, volume is in very as volume as a powerful tool. Systematic method, practical use, and advantage learning. To wrap up, double integral provides us a very systematic method for calculating complex volumes. There are practical uses across physics, engineering, and computer graphics. Mastering double integrals open the doors to advanced calculation topics and real world problem solving. Thank you for listening. I hope it helped you to see how powerful and versatile double integration can be.